So let's talk about machine learning, which is, to me, it's been something that looked like magic for the longest time. I was doing software, but I had no idea how a computer could caption photos, for example, or understand text. To me, it was absolutely out of my scope. I didn't know how it worked. So if it doesn't look magic to you, then you probably already know too much for this presentation. Sorry. And this is the basics. Machine learning explained to humans, where by humans I mean developers. And I will try to keep the mathematics intuitive wherever I can. So people, all the people who are very comfortable with math, I'm trying to keep it simple, maybe even simplistic at times. This is not training in machine learning, okay? I don't aspire to teach you machine learning in 40 minutes, just to demystify it, to remove magic, and show you how it can actually work. So let's have a simple example. Let's say that we have a small restaurant, a pizzeria, and every day in the afternoon, we have a certain number of reservations. Let's call it X. And every night, we sell a certain number of pizzas. Let's call it Y. And these two numbers are related, okay? And the idea is I want to write a computer program that learns the relation between X and Y and can then predict Y from X. Like I have 25 reservations today. How many pizzas can I expect to sell? You can expect to sell 40 pizzas. Okay, let's prepare enough dough for it, for example, okay? So the first thing that I do is to collect examples, to collect data for the computer to learn from. So here is a file with a number of examples, a number of days. On the first day, I had 13 reservations. I sold 33 pizzas, and so on and so forth. Let's say I have a few dozens of these, okay? And the first column is my input variable, the variable I want to predict from. And the second column is called the label. This is a weird machine learning vocabulary. It's like, imagine that somebody went down and labeled each number of reservations with the matching number of pizzas, okay? I want to load this data in a computer program. And, well, I wish I could use Ruby. Yesterday, there was an interesting discussion during Charles' presentation about is Ruby ready for machine learning? We all hope it will get there eventually. Right now, it's not, I would say, so I used Python. So, whatever you think about Python, whether you like it or not, you will have no trouble reading Python code. So it's a good choice. Also, I don't want to go against the flow and give you examples that are weird. I will just use NumPy, like pretty much everybody does. NumPy is a numerical library. It's not a machine learning library. I want to use machine learning libraries. I want to show you the internals of how it works, okay? And now I'm just loading the data. It doesn't matter how I load it exactly. What matters is that I have two arrays. One contains all the reservations, and the other contains all the pizzas. Looking at numbers is not a good way to understand how these numbers relate. So let's plot a chart instead. Reservations against pizzas, and if I just dump my data over this chart, now you can see the relation, right? You can see that as we expect, in general, more reservations mean more pizzas sold. Now the problem becomes, how can I write a computer program that takes this data and learns the relation, and then uses the relation to do inference? And there is a very classic way to do this from statistics, from way before computers, that works like this. It works in two phases. Phase one is look at the data and trace a line over the chart that approximates the data. It doesn't have to be perfect. In fact, it's not going to be perfect unless the data happens to be exactly aligned to begin with, which is probably never going to happen in any interesting case. This is just an approximation. But it's good enough in this case, because the data happens to be roughly aligned to begin with. The second phase is forget about the data entirely, just to use the line and use it to make predictions. For example, I have 25 reservations. How many pizzas do I expect to sell? Let's trace all the way up to the line, then all the way left to the pizzas, and the 22 pizzas. Of course, that's just a coincidence. So this is the number of pizzas that I expect to sell tonight for 25 reservations, okay? So now, this is called the linear regression. Regression is the word that statisticians use to say, predict the value of a variable from another variable. And it's linear because I'm using a line instead of, I don't know, some kind of complicated curve. Now I need to write a computer program that does linear regression. And to do that, let's recap how linear regression works. First, approximate the labeled data with the line. Second, use the line to make an inference about unlabeled data, a reservation without the pizzas. This is going to be a bit of a refrain, okay? These two phases. Let's start implementing from phase 2, because it's easier like this. Because phase 2 assumes that we already have the line. So now we have to decide how to represent the line in software. One way to do that is just to use the equation of a line. You might remember it from high school. Maybe you were using different symbols for it. Y equals something by x plus something else. You might have been calling these two parameters, which I call W and B. You might have been calling them A and B. It doesn't matter. I call them with these weird letters because, once again, machine learning vocabulary. W is called the weight sometimes, and B is called the bias. Just take it as it is. You don't need to remember this stuff, and you don't even need to make much sense of it. If you want some intuition, in case you can't remember this stuff, W is how steep the line is. You can see that if you get a bigger W, then for the same number of pizzas, X, you get more, reservations, you get more pizzas. So it's like moving the line like this. And the B is like shifting the line up and down, okay? So that it can move around. But that doesn't matter. You can just say this is the formula. It has two parameters. By changing these parameters, I can change the line. These two parameters are the line, okay? They identify the line. Let me change one tiny thing. I added a little hat on top of Y to distinguish this Y, which is the number of pizzas we expect to sell, from the previous Y, which was the number of pizzas we actually sold, which is a subtle difference, but it's useful to avoid confusion, okay? So now, if I have a line, I can say I have 25 reservations, okay? X is 25. How many pizzas do I expect to sell? Well, let's say that this line has these parameters here. At this point, I can just replace the stuff, okay? I can just do the math, and I get 42. So the code to do this is actually a one-liner. It's a function that I called infer that takes the pizzas. Sorry, again, it takes the reservations, X, and then it takes the line, W and B, and it returns the number of pizzas. Okay? So this was the easy part. The second part of linear regression is done. That's a one-liner. The first part is a bit tough, so I would have to ask you to focus with me for like 10 minutes. How can I look at this data with a computer program and find the line? How can I find the W and B, the best line that approximates the points? The first thing that I can notice is that any line that I find is going to be wrong, right? It's an approximation. It's going to have an error. Let's make a concrete example. Here are our data again. So let's pick one random day, like this one, 14 reservations, 32 pizzas. This is that point. This is a real piece of data. This is data that we measured. But if we have the line, and if we use the line to do this measurement, then we would say, hey, we have 14 reservations replace W and B, and if we use the same line that we used before, we get this number, which is not the same number, right? It's there. There is a distance here. This orange thing is the error. Now, let's write a function that calculates the error over all the points. Weird machine learning vocabulary part 4. This is called the loss. Whenever you see loss, this means the error, essentially. And the loss is going to take all the examples, X and Y. And it's going to take a line. And it's going to tell us a number that says, this is how much you screwed up. This is how wrong this line is. The higher the number, the higher the error. OK? How can we do this? Let's first take all the points and make inferences for all the points. This is why we're using NumPy, by the way. NumPy is very good at doing the same things, the same operations on arrays that you can do on regular numbers. So when I say infer x, w, b, and x is not a single number, but all the reservations, it will calculate all the y hats. And when I say minus y, then it's two arrays, and the subtraction of two arrays is the subtraction of each element from each matching element, OK? This all counts for free. Otherwise, I would have used the Ruby, essentially. So, OK, these are the errors, and it's an array of errors, OK? Now, one thing to notice is that some of these errors are going to be positive, some are going to be negative, depending on whether the point is above the line or below the line. And the negative error doesn't make any sense. First of all, I don't want positive and negative errors to cancel each other out. So let's make them all positive by squaring them, OK? Just like in Ruby, this double star is the power operator in Python. And now that we have this squared error, let's average them. This is a NumPy operation. And boom, we have a loss. Now we have a gauge. We have a function that says how wrong a line is. Now we can use this function to find the line with the minimum loss. Notice that x and y are not really variables. They never change. We collected them once and for all. So the only variables are w and b. And we want to find the w and b that result in the best line, the lowest loss, OK? So how can we do that? What I did was to plot the loss, to just draw a chart of the loss, to see what it looks like. And here it is. You have the bias and the weight, b and w, and you have the loss. And you can see this nice, smooth surface, OK? And the place where we want to be is that place there, the lowest point in the loss, right? How do we get there? This is probably the most important algorithm in machine learning. And it's actually quite intuitive. Here is how it works. Let's start somewhere. Any point will do, OK? Let's say we start here. And then let's use this wonderful mathematical tool that's called the gradient. The gradient is essentially how sloped the surface is. To do this in practice, what we do is to slice the surface like this, OK? We can fix W and move B, and then we can fix B and move W. We get these two curves. Each curve is a gradient. We calculate these gradients with a tool that is called partial derivatives. Might ring a bell, OK? So essentially, we get these two arrows. The gradient points uphill by convention, just because of the way partial derivatives work in mathematics. So what we do is we revert these two, because we want to go the other direction, right? We want to go downhill. That's the place where we're going. Then we probably multiply these two by some factor to make it smaller, because we don't want to move too fast along this surface. We don't want to, overshoot the minimum. We want to get there in tiny steps. And then we move W and B to this new position. And then we do it again, and then we do it again. And then we do it a few, I don't know, hundreds, thousands of times. And as we get closer to the minimum, we take smaller steps. That's how the gradient works, right? At the minimum, the surface is flat, so the gradient is 0. And at some point, we are close enough, we have a good enough approximation that we don't care anymore. So essentially, this is what happens, okay? Like a ball rolling over this surface, we go towards the minimum until we stop there. And that's our WMB. That's the line that we're looking for. This is called the gradient descent. In our case, it's just a tiny little surface. If we're talking about some, very complicated Google artificial intelligence system that, I don't know, recognizes and labels pictures or pilots bomber drones, then it's probably going to be a very, very complicated multidimensional surface. Still the same thing. It's still gradient descent they're using, okay? Or some variation of gradient descent. So let's look at the mathematics behind it. This is just a mathematical notation for the loss. If you are not used to mathematical notation, it might look complicated, but hey, Wx plus b is just y hat, right? It's just the line. And we subtract it, so we subtract it from the label, this is the error, we square it, we average it, it's the mean squared error, the same loss that we had before, okay? And then we can calculate the partial derivatives. Some of you will just do it mentally. For the rest of us, we just pick up a math book and we look them up. These are the two partial derivatives. So converting this stuff to code is not that hard. The loss, we already had it. This is the same function we had before. I just squashed it in a single line. And the gradient is something like this. It's calculating the gradient for W and the gradient for B, and returning both gradients. And now all we need is the implementation of gradient descent, which is this piece of code here. Okay? It takes the examples. It takes a certain number of iterations. It takes alpha, which we will see in a moment. Then it initializes W and B at any point, in this case at 0. Then it gets into a loop. It prints the loss, so we can see the loss decreasing. We can check visually that it's decreasing. It calculates the gradients, reverts them, multiplies them by this alpha to make them small, uses them to increment W and B, does that a lot, many, many times, and then returns it. So this is the second part of gradient descent. Let me show you how it works in practice. This is exactly the code we've been seeing. The infer method, the loss gradient, and find best line methods. Then we're loading the data. We are doing 10,000 iterations with a pretty small alpha to find the W and B, to find the line. Then we're using the line to say we have 25 reservations. How many pizzas do we expect to sell? We print that stuff on the screen. Then there is some code to plot the data and plot the line so we can see that it's working. And if I run this stuff, boom, you can see that the loss is decreasing at every step. It's getting smaller and smaller as the ball rolls over the surface and gets closer and closer to the minimum. And at the very end, we have this line, which means that for 25 reservations, we expect to sell 40 pizzas. And if I press here, nothing happens. No, it does. Nice line, man. And this is it. This is how it works. This is how linear regression works. And now that you know what the two phases of linear regression are, believe it or not, you know how machine learning works. Because that's it. Yeah, sure, linear regression, that's super simple, right? It's stupid simple, and people are like, yeah, linear regression. Everybody knows that. But actually, okay, maybe when you are doing stuff like recognizing and labeling images, you are not using a line. Maybe you're using a much more complicated function. A line has just 2 parameters. This very, very complicated surface might have thousands or hundreds of thousands of parameters. All these weights, okay? But the idea is the same. You start from a random place, or a pretty random place, and you look at the surface, and you try to apply this surface, this function, to the data, and you're like, no, this sucks. It doesn't even come close. Let's make it a little bit better. And you start stepping down its gradient. And you make it a little bit better. And yeah, in our case, it took very, very little time on my humble computer, while fitting that very, very complex surface might require a huge amount of time on a huge rack of GPUs in some Facebook processing center. But it's the same idea. You twist and bend this surface until it fits the data. And once it fits the data, what you have done is the training part. Now your computer has been trained. Now the system knows those weights, because that's the only thing that matters. If you know the weights, now you can just take the weights, replace them in the function, together with the data that you're trying to identify. For example, hey, here's a picture. That's the data. Which kind of objects can you see in this picture? You put the picture in the system, together with all the weights, boom, you get a result. This is the inference phase. And it's super cheap. You know, training takes a long time, but inference, in our case, it was a one-liner, and it was fast. That's why my cell phone can recognize my face. Training that system to recognize faces probably took a lot of processing power, but doing it, okay? Now, I might stop here and do the easy job, because that's machine learning for you. But of course, some of you are probably going to be rightly skeptical, like, yeah, sure, Bozo, this is like a toy example, right? But getting from here, from this thing about pizzas, to recognizing images, for example, to computer vision, I mean, there must be more to it. It cannot be just like this, right? And in fact, there is more to it. But actually, that additional stuff just makes things better. But you can get surprisingly far with these notions alone. So now I want to show you how far you can get, actually. So, oh yeah, this is for myself, because I would forget to do this. So, yeah, because running this code takes a while, and I'm going to run it in the background as I keep talking, and then show you the result at the end. I will also explain the code as I go. I see a loss, that's decreasing. That's a good sign. OK, so I drew this map. I actually looked on Google for how to draw a map, because I'm that kind of geek. And the idea here is that we are here in linear regression land. And we want to embark on a big, epic travel to reach the beautiful land of computer vision. And I want to show you just which path we're going to follow. I don't want you to understand every step. That would take more time. Actually, half a day would be enough. But right now, we only have a fraction of that. So let's just show the high view. And I don't expect that you will understand or certainly not remember every step. Just want to show you that it's not rocket science. So first, we're in linear regression land, but the example I gave you is super simple. I mean, most real-world examples don't have one input variable. They have more than one input variable. Like, for example, our pizzas the pizzas we sell might depend on reservations, yes, but maybe also on the temperature of the day. Is it warm? Do people go out and it out. And maybe the number of tourists in town might also be a factor. Maybe we scraped this number on a scale from 1 to 10 from the local tourist office site, okay? So we have many variables. So what happens to linear regression then? First of all, instead of having just one array as an input, now we have all these numbers as an input. So our input is a matrix now, right? One row per example, one column per variable. And if you look at the line, so far we had the reservations and pizzas. So we could put these on a three-dimensional chart, trace a line, and use its equation to calculate y hat, our inference. If we add another variable, we have to add a dimension, right? Now our points are points in space, in a 3D space, rather than points on a plane, because we have, for example, reservations and temperature as input variables, and then we have the pizzas as the y-axis. So how do you approximate points in a space? A line is not enough anymore. You need one more dimension. You need a plane to approximate this stuff. And you can use the equation of a plane that happens to be like this. Essentially, it's like a line, only it has one more weight, because it has two variables which have different weights, right? Even intuitively, the weight of the temperature is probably not the same weight as the reservations. So, and we can keep adding dimensions. If I add another dimension now, I would have to show you a four-dimensional plot, but I don't really know how to draw that. So here is a picture of my head exploding instead. But the formula is the same. I mean, I just keep adding weights with the number of variables. I'm going to do it now, eventually. I will do it like this.
It's a well-known syndrome of live demo.
As soon as I get like 1 minute of live demo into it, shit happens. It's never do it. Was the pace okay? Is it interesting? Are you curious to see the code running when eventually... Yeah, my computer apparently choked on it. I really hope they announce a new Max tomorrow. I think it's about time. I've been resisting that because of the shitty keyboard. But... that's not the problem, mate. Thank you. The problem is simply that the entire computer seemed to choke a bit.
He's freezing, yeah?
And that's what I have to do, I'm afraid. Don't worry. Let's just do this. I will restart the computer. And while it's restarting, and I'm restarting the code, I can just take questions about the first part of this presentation. Hey, take it easy, guys. Let me restart. OK. Just sorry if I don't make eye contact, but I'm trying to restart this thing. If it starts installing an operating system update, then I'm sorry, but it's just God not wanting. Yeah. No, it's not Windows, mate. I swear.
Check.
Yes.
Hi. Would you run your code once again?
Are you trying to put me in a tight corner? Yes, I would. I would, of course. Give me time. It's an old Mac.
Hi, can I ask?
Sure. Hey.
You said that Ruby isn't suitable for machine learning now. What should happen to it
Yeah.
to be?
I mean, There are a few reasons why I think is. Of course, I went to Ruby because it's my favorite language. Because when I started to learn machine learning, there are two main reasons why I don't think that Ruby is the best choice now. Reason one, it's just going against the flow. Everybody's using Python. You go to the community, they will give you Python snippets. Sure enough, it's shitty Python code because most of them are mathematicians, not coders. They cannot name a variable for their own dear life. But, sorry, mathematicians in the room. But, matter of fact, the code that you get, the examples that you get, that's all Python. So using Ruby for that, it's a little bit like going against the grain. It's just not worth it when, okay, Python is an okay language. It's not my first choice, but I'm fine with being multi-language. I don't mind that much. In the meantime, I'm restarting that code. And that's the first reason. The second reason is that, done, restarted. The second reason is that the libraries in Ruby are not quite ready yet. I mean, Python has, for example, stuff like NumPy. NumPy is, well, it's frankly a horrible library from the point of view of APIs. It's really terrible. But it works. It gets the job done, and it gets the job done fast, and it can use your GPU to get the job done, for example. I looked for equivalent libraries in Ruby, and I just couldn't find any that actually did the job the same way. I'm sorry. So in the end, I was like, yeah, it's just more expensive to try and use Ruby for that than to just bite the bullet and use Python. It's not ideal, but hey, I've been done Visual Basic back in the day. That was Vietnam compared to these. I don't care. I will just use Python, okay? Did that answer your question? Okay. Okay.
Do we still have time for questions, or are we going to continue?
One more.
Okay, one more.
Okay. Hi, my name is Alex. Thank you for the speech. Very interesting.
It's not over yet. Wait until it's over before you thank me. It might suck in the end.
No problem. It's always problem with demo. They stacks, they freeze, lagging. The computer suddenly shut down, reboots, and so no.
My computer.
It's okay. I have two questions. First question: is any machine learning algorithm use neural networks?
Yeah, neural networks is a machine learning algorithm. Mm-hmm. I mean, actually, what I just showed you, the thing that does linear regression, mm-hmm. In a way, I'm abusing the terminology a little bit, but in a way, what I showed you is a perceptron, the basic unit of machine learning, or at least one kind of machine learning. I'm also abusing the term machine learning. Let me be a bit more precise. This is not machine learning. This is a specific type of machine learning. It's called a supervised learning. It's supervised because there was a supervisor, that is a human that labeled the data. There are other kinds of machine learning. On the other hand, this supervised learning right now is the cool machine learning, okay? The one that recognizes cat pictures. Yeah. So this is the basic of it. Then you take this basic, you have many of these perceptrons, you mount them together, you get a neural network. Any machine learning researchers would kill me because I oversimplified the fuck out of it. But you catch my drift.
Okay, thanks. And second question, is there some alternatives to artificial neural networks for machine learning?
Plenty of them. There are a lot of algorithms. In fact, for the longest time, people thought that neural networks probably were not the best way to do this kind of stuff.
And that's why I ask this question. So is there any alternatives
Well, you know, it's technology. Some things seem to be the underdog, some ideas, right? Functional programming has been the underdog for 50 years before somebody was like, hey, this stuff works, let's just use it. Something similar happened with neural networks. In the last few years, people found out ways to overcome the limitations of neural networks. So they started doing stuff with neural network that is just crazy. And right now, neural networks are going through a renaissance, and essentially they became the thing, the place where innovation happens. Will they stay like that, or will they be replaced by another algorithm? We don't know. At the moment, there is a lot to do in that field.
Mm-hmm. So, in summary, there is alternatives, and for now it's in under research. Yeah. Okay.
Yeah. Yeah. I mean, this stuff is a moving target. Every day, every other day, there is a new great research happening, and they find out new amazing things.
Okay. Thanks.
Thank you. Continue.
Hopefully. So this was the last equation we had, the equation of a plane, and I was like, okay, even if I cannot make a picture of it, I can just keep adding variables to it, and I can keep approximating these points with more and more variables. Right? That's where we were. So this is the equation that I can use, and once I use this equation instead of the equation of a line, I can do linear regression with as many dimensions as I want. Now, as a programmer, I'm particularly annoyed by this B term now, because you can see that all the rest of the equation is very uniform. But this B term is kind of sticking out and forcing me to write specific code. So let's get rid of B. There is a quick trick to do it. It doesn't matter whether you remember it or not. It's just one quick way to get rid of it. I will just take the input data, add another column to it that is called the bias column, and it's full of ones. And the reason for that is that now I can take that equation. It's the same equation. I just moved the B to the beginning of it. And I can rename B to call it, I don't know, W0, like another weight, and multiply it by the first variable, which is always 1. Trick. There goes B. Okay? Now it's a completely uniform equation that is called the linear combination of weights and variables. And the linear combination happens to be something that I can implement with one line of code in NumPy. It's an operation called the matrix multiplication of x and w. Okay? So actually, the inference method became even smaller and simpler with multiple variables. And this is how we took our first step. We went for simple linear regression with one variable, all the way to linear regression with multiple variables, which is called sometimes multiple linear regression or multivariate linear regression. It has different names. But this is how we can tackle real-world problems rather than my toy pizzeria problem. Step 2 of 3. So far, we have been forecasting, inferring variables that are like pizzas. They can take any possible value. Okay? Well, okay, pizzas are always integers, but actually we got fractional pizzas and we didn't care. So this is a continuous variable by all practical terms. And what happens is that if we try to predict something that is not continuous but discrete, because you know cat pictures are discrete, your face is discrete, it's either yes or no, it's binary actually, and discrete is actually where the action is at. So let's try with a discrete variable like break even. It's a binary quantity that says whether or not we break even, we make enough money to cover our expenses for the day. This might look like, hey, it's the same thing, right? Just apply linear regression to it. But if you plot this data, you will find something like this. How am I supposed to draw a line that approximates that? Those points are not on a line. So yeah, linear regression as it is cannot work here. we need to give it a little boost. Like this, we can take this function and wrap this function, the linear combination, into another function that squeezes it into the range 0 to 1. And then that boosted version of linear regression can work here. Such a function would be like this. Here we have any number, right? And it would map any number to this narrow band, 0 to 1. And there is a function that is just perfect for these, and it's called the sigmoid. It goes like this. You know, very big numbers become a 1. Very small or very big negative numbers become 0. And everything in between is sitting across this smooth line. And implementing the sigmoid is actually quite simple. I will spare you the mathematical formula. Again, I don't want to show you the details. I just want to give you the gist of what's happening here. So we have the linear combination. We do that formula around the linear combination. Sigmoid. Now our output is constrained to be 0 to 1. And we can clip it. Is it closer to 0 or closer to 1? We just say, hey, it's at 0.6. We break even. It's 0.9. Fuck, we break even, okay? So there is a side effect in using a sigmoid, though. And the side effect is that you remember the loss, how the mean squared error loss, how smooth and beautiful it was. It makes you want to roll over this surface like a ball to reach the minimum. But once you have the sigmoid in the picture, this is what you get. Look at all those nooks and crannies and valleys. You can see that gradient descent wouldn't really work here. It would get stuck in a local minimum, one of those holes. So we need to change the way we calculate the loss. That's not a big deal. The machine learning literature, the statistics literature, in fact, has a lot of ways to calculate the loss. So we can just move from these equations, that are pretty much what we used before, to these other equations, which are, again, I won't explain in detail. I'm just showing them to show you that there is no huge growth in complexity here. I'm just using a different method to calculate the loss. This is called the logarithmic loss, and that's its gradient. And once we do this ugly, uneven terrain becomes like this. Okay? So now we can roll over it like a field of grass. And this is the second step. We went from multiple linear regression to something different that is called logistic regression, because the sigmoid is also called the logistic function. That's the name, the traditional name in mathematics. We have one last step, and then I'm done. And the last step is, okay, but how do we do computer vision with this stuff? This is the MNIST database. It's a standardized benchmark for computer vision. It's essentially a data set of 60,000 images, each of which is the picture of a handwritten digit. They look like this. Here is a small selection. I'm showing it to make a point, to make the point that this is not artificial data that is particularly nice. This sucks. This is the real thing. Okay? Some of these numbers, some of these digits are hard to read for you. So if our computer code can actually work with this thing, then we are onto something. I'm creating suspense. What I'm doing actually is to check that the code is running in the background so that I can finally show that it worked. Let's hope it doesn't get stuck again. So each one of these images looks like this. It's a 28 by 28 pixels image, where each pixel is 1 byte, which represents a tone of gray from 0 full white to 255 full black. Or is it the other way around? Doesn't matter. And it's labeled, of course, supervised learning. Somebody took the trouble, went to the trouble to label all of these images with their matching number. How can we take this image and turn it into something that we can feed to our logistic regression program. Here is one way. Take the image, squash it into one long line of pixels. Each pixel becomes its own input variable. Yes, we have 28 by 28 input variables, plus one for the bias column, if you remember about it. Suddenly, we have a lot of input variables. This is a 785 dimensional problem. Okay? We have computers for that. 60,000 lines, one per example. How do we encode the label? I'm going super fast here. Again, just to give you an idea. So far, the labels were an array. One array per label. One element, sorry, per label. But now we have a label that is not just binary. It's a label that can go from 0 to 9. How can we encode the things that go from 0 to 9, that take a number of different values? Here is a trick. Let's have 10 columns, where each column is a classifier for that specific digit. So the first column is essentially a classifier for zeros. The second column is a classifier for ones, and so on. Which means that if I'm encoding a 4, all of these are going to be zeros, except the 4 classifier, which is the 5th column. And each row, each example, in this, each label in this matrix will have all zeros except for a single one. This is an encoding that's called the one-hot encoding, because only one of these is hot in each row. What happens when we do inference? Well, it's like having 10 classifiers here. So we are going to get 10 inferences, one for each classifier. And what we do is to look at these numbers and just take the maximum number. Because it's like here, hey, 0 classifier, is this at 0? Oh, 0.029. It's like, no, this is not at 0. One classifier, the same. The one that looks like there is a chance is the 4 classifier. And that's what we take. This must be a 4. Okay? Finally, the last matrix, the weights. Sorry, you might remember that we had one weight for each input variable, which is 785 weights. Now we have one set of weights for each classifier, for each binary classifier. That is 10 of them. Suddenly, we have thousands of weights. We are already approaching a real-life problem. Okay? So let's recap. Here is the code. Let me see how much time we have. Perfect. So code. We have the sigmoid, linear combination plus the sigmoid, rather. The loss, the gradient, you have seen these. The inference, this code is just saying, hey, make an inference. There are 10 of them for each line here. Let's take the max for each line. Okay? We have the train method, which used to be called the find best line. Now it's definitely not a line anymore. Okay. And then we are training the system until we get this big matrix of weights. That W is a 785 by 10 matrix of weights. The training is over. Now we can do inference. And we do inference on the MNIST test set. MNIST comes with a smaller set for testing so that it's a different images, so we can be sure that it's actually learning how to recognize handwritten digits. And we do a comparison there, and we see which percent of images we recognize. And the reason I'm showing you this code is just to show you how short it is, actually. This is all of it. And actually, if we remove inference, which is not necessary, if we remove this reporting code and all the other code that we don't need the loss, actually. It's just for reporting. And this linear combination here, I can inline it. I'm going to obfuscate it a little. I just start removing everything that is not strictly necessary because, hey, sue me. And here, the inferences, I can replace them here. I can replace this thing here. Yeah, I'm on a roll. I want to see how short I can make this code. And still, of course, have it barely readable. And this is not necessary, this is not necessary, this is not good. Yeah, okay, it's this code. This piece of code, okay? This is the code that is learning how to recognize handwritten digits. It's these 20 lines of Python code, and you recognize, what do you mean 5 minutes? I thought I had the entire day. Yes, yes, I will, I'm gonna include. And, and this code, you could understand all of it. Or at least give me another couple of hours. You can understand every single line, find alternatives. There is nothing magic in these 20, why 20? 19 lines of code, okay? And this code recognizes handwritten digits with an accuracy of 90.32% at the moment. So this is it. It's not rocket science, okay? Okay, so that's it, the last step, and we did computer vision, and you know how it works now. It's not magic anymore, I hope, and thank you, everybody, okay? Thank you.